Hi, my name is Nandan Singhani, and I'll be going over Lab 2 of Physics 2212, which is titled Lines of Charge. For some background on Lab 1, we observed that the physical interaction between ordinary objects can create an excess or deficiency in electrons, resulting in a net positive or negative charge. The objective of Lab 1 was to create charged pieces of tape and to observe the interactions between the tapes and other objects. The goal was to determine the charge of the charged tapes by using a point charge model. The calculations from Lab 1 resulted in a tape charge of 1.86 times 10 to the negative 8 coulombs. For Lab 2, we wanted to more accurately determine the charges of the pieces of tape by using distributed line charges and superposition, along with computer modeling using GlowScript. The line charge model resulted in a charge of 3.328 times 10 to the negative 8 coulombs, which was 1.78 times larger than the charge from Lab 1. The main physics principles used in Lab 2 include Coulomb's law, which quantifies the electric force between charged particles. Coulomb's law also tells us that like charges repel and opposite charges attract. The lab also highlights Newton's laws of motion, including the second law, which states that force equals mass times acceleration, and the third law, which states that every action has an equal and opposite reaction. The lab also follows the law of conservation of charge, which states that a charge cannot be created or destroyed, only transferred, as well as the superposition principle, which states that the combined charges of an object is the result of summation of individual charges distributed along the object. The method followed to produce this lab involves charging a piece of tape. First, lay a tape with length of 20 centimeters over base tape with similar length. Then quickly pull this tape off the base tape, creating a charge tape. To test the charge, hang the U-tape off the edge of a desk and bring your hand near. If the tape is attracted to the hand, it is charged. Similarly, you can test the specific charge of the tape by rubbing a plastic pen through hair to negatively charge the pen. Then, hold the pen near the U-tape. If the tape is attracted to the pen, it's either positively charged or neutral due to Coulomb's law. In order to test charge tape interactions, first set two equally sized objects near each other on a table. Then place the U-tape over top the objects, bridging the gap so it's hanging in between. Next, hold a second charged tape by its ends and bring it below the first tape. Slowly move the tape closer to the upper tape until the upper tape begins to float upwards. Measure the distance when the tape first begins to float. We will use this distance to help determine the charge of the tape. The lab is constructed based on certain assumptions. Firstly, we will not be treating the charges along the piece of tape as a single point charge. Instead, we will treat them as a distribution of charges. We are also assuming each charged piece of tape we created has the same net charge, evenly distributed along the tape. We are then assuming that air resistance is a negligible force on the tapes, and that the mass of the tape can be accurately ratioed based on the length of the tape. Finally, we are assuming that rubbing a pen in hair causes it to become negatively charged. During the lab, some observations were made around the interactions between the tapes. The two main forces that were acting on the upper charge tape in the y direction include the electric force from the lower charge tape pointing upwards, as well as the gravitational force pulling the tape downward. Since the momentum of the upper tape was not changing during the experiment, it can be assumed that these two forces were equal due to Newton's second law. The measurements of the experiment include the length, width, and mass of the tape, which are shown on the slide. The measured distance between the floating charged tapes was 0.04 meters. The calculations from the experiment for the upper charged tape include the force of gravity, which is 0.001962 newtons in the y direction, and the electric force from the lower tape on the upper tape, which was equal in magnitude to the force of gravity due to the net force on the tape being zero. For the previous calculations for the results of Lab 1, the tape charge was calculated to be 1.86 times 10 to the negative 8 coulombs. This was easily calculated using Coulomb's law as the entire tape was treated as a single point charge. In order to calculate the charge of the tape more accurately, we will be using a distributed charge calculation using GlowScript and VPython. We will first create a function to calculate the force of gravity on the top tape. Next, using the calculated charge from Lab 1, we will determine the magnitude of the electric force on the top tape by using a superposition model. In order to do this, we will be using a function to split the tape evenly into n charges, with each holding a small ratio of the total charge of the tape. The n electric forces are then calculated and summed up to get the total electric force of the tape. We then adjust the charges until the magnitude of the electric force is equal to the magnitude of the gravitational force on the top tape. The GlowScript code begins by establishing the values of the gravitational and Coulomb constants, as well as the mass and charges of the tapes. The following function creates and models a line of charges for both the top and bottom tape. The function splits each tape into n separate charges, where n is set to be 20 in this case. The final function iterates through each of the separate charges for both the bottom and top tapes and calculates the net electric force on the top tape due to the interactions between each separate charges within the two tapes. The result of this line charge calculation returned a new net charge of 3.28 times 10 to the negative 8 coulombs, which is 1.78 times larger than the point charge calculation. If we compare the GlowScript models, the new model shown on the right more accurately depicts the charges on the tape as a line of charges. The green arrow shows the electric force on each individual charge as a result of the bottom tape. The white arrow is the summation of these individual forces as the net electric force, which is equal in magnitude with the gravitational force. To summarize, the charged tapes were positively charged, with a net charge estimated to be around 3.28 times 10 to the negative 8 coulombs, calculated using the line charge model. Compared with the point charge model, which estimates the charge to be around 1.86 times 10 to the negative 8 coulombs, the line charge model estimate is 178% larger. These charges differ since the point charge model generalizes all charges along the tape into one charge, when in reality they would be more evenly distributed along the tape like the line charge model. The line charge model is therefore more accurate since it takes into account the interactions between the charges spread across the tape and utilizes superposition to calculate a more accurate charge. If we were to determine an even more accurate charge, we would increase the number of individual segments of charge to infinity. This would be calculated using an integral, as computer modeling can only create a definite number for n. Thank you for watching.